Hi, this is Dr. Bay, and here's Bugsy, and today we'll be going over the conformations of cycloalkanes. We'll delve into how to draw cyclohexanes in a chair conformation and what exactly determines each conformation stability. So stay tuned.
Organic chemistry,
Taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly reply, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Just as review from learning about Newman projections of linear alkanes, steric interaction again is the repulsion between two atoms or a group of atoms when they are way too close to one another, and this interaction is prominent especially in staggered gauche conformations. A new type of strain that we're going to learn about today is called ring or angle strain, which is the increase in energy associated with a bond angle that has deviated from the preferred angle of 109.5 degrees. If each of these cycloalkanes were completely planar, they would have the following CC bond angles. And based off of this theory developed by Adolf von Baeyer, five-membered rings should have almost zero ring strain, while both smaller and larger rings should be slightly strained. Eventually, his theory did not hold true because these cycloalkanes are actually not planar and position themselves in a three-dimensionality to achieve the lowest energy conformation. And to do this, a lot of these cycloalkanes pucker, and we'll discuss the effects of puckering throughout this video. Cyclopropane has two main factors contributing to its high energy: angle strain from having small bond angles and torsional strain from eclipsing hydrogens. Cyclopropane has significant ring strain because its CC bond angles are compressed from an ideal 109.5 degrees to 60 degrees, and it has a large torsional strain because the ring is locked in an eclipsed conformation as seen in a Newman projection along the C1-C3 bond. So because of all of this strain, it makes three-membered rings highly reactive and very susceptible to ring opening in order to alleviate its strain. Cyclobutane is lowest in energy when its geometry is puckered into a butterfly conformation, as seen in the bottom right corner. It has more torsional strain than cyclopropane because it has four sets of eclipsing hydrogens rather than just three. Puckering from a planar square shape into a butterfly conformation reduces torsional strain but increases ring strain from 90 degrees to 88 degrees. Cyclopentane takes on a puckered envelope conformation, and its puckering reduces torsional strain but increases ring strain. Cyclohexane can take on multiple different conformations: chair, half chair, twist boat, and boat, and each of their respective energies are shown below them. But we're going to focus on two main conformations, the chair and the boat. So let's fill in all 12 hydrogens around the chair conformation. We actually can also draw Newman projections of rings, but we just have to look down two specific bonds rather than just one. So let's analyze the C2-C3 bond as well as the C5-C6 bond. You can see that a chair conformation places all of the hydrogens in a staggered Newman projection, which explains why the chair has the lowest energy. But if we fill in all the hydrogens for the boat conformation, you can see that a lot of the hydrogens are eclipsing, and one particular interaction is between the C1 and C4 positions, which is called a flagpole interaction. It's essentially a steric interaction between hydrogens on both sides of the ring. And if we look down the same two bonds for a Newman projection, we see that there are several hydrogens eclipsing with one another, which is why this conformation is extremely unfavorable. And that's shown by the increase in energy by 30 kilojoules per mole in the boat conformation. Now let's look at an energy diagram to compare all the cyclohexane conformers, where the x-axis is the reaction coordinate and the y-axis is the potential energy in kilojoules per mole. And we have to see that the chair conformation is most stable at 0 kilojoules per mole. It then goes up to 45 kilojoules per mole to make the half chair, back down to 23 to form the twist boat conformation, up to 30 kilojoules per mole to form the boat, down to 23 to form the opposite twist boat, up to 45 to form the opposite half chair, and back down to 0 kilojoules per mole to form the opposite chair conformation. But since the chair is the lowest, most stable conformation of cyclohexane, we're going to focus on how to get from one chair to the other chair. First, let's learn how to draw a chair conformation. Step 1 is to draw two parallel lines pointing towards the right top corner. Step 2 is to draw one line from the top left going towards the bottom right. Step 3 is to draw one line from the bottom right going towards the top left that is parallel to the last line that you just drew. And step 4 is to connect the dots and draw in the last two lines, making sure they're parallel to one another. There are two types of bonds in a cyclohexane chair conformation. There are equatorial bonds that are in the plane of the chair, and they're drawn slanted as shown in blue. And then there are axial bonds that point vertically up and down, shown in green. And if we draw the skeleton of the chair, we can number each carbon atom starting from number 1 in the top right-hand corner, and then go around the chair clockwise and label the carbons accordingly. The first axial bond on C1 will point upward, which is shown as a vertical green line. The second axial bond on C2 will point downward. And as you go around the chair clockwise, axial bonds will alternate going up and down, but will always be drawn vertically. So the third axial bond on C3 will point up, the fourth will point down, the fifth will point up, and the sixth axial bond on C6 will point downwards. Now the equatorial bonds will point in the opposite direction as axial bonds and are drawn slanted or in the plane of the chair. Each equatorial bond will be drawn parallel to the bond in the ring that's 2 bonds away from that carbon atom. So at C1, the equatorial bond in blue will point down to the right, since the current axial bond in green is already pointing up, and it will be drawn parallel to that of the C2, C3, and the C5, C6 bonds. At C2, the equatorial bond will point up to the right and will be parallel to both the C3, C4, and C1, C6 bonds. And then again, as you go around the chair clockwise, equatorial bonds will alternate between pointing up and down. That said, the third equatorial bond on C3 will point down, the fourth will point up, the fifth will point down, and the sixth equatorial bond at the C6 position will point up. Let's draw both chair conformations of bromocyclohexane. Draw the first chair conformation using the 4 steps that we had just talked about, and then place bromine at the C1 position. Large substituents that are bigger than hydrogen are more stable at the equatorial position. So that said, we'll draw bromine going downwards at an equatorial bond. Now to draw the second chair, we're going to draw the skeleton of the chair in the opposite direction, which essentially is called ring flipping the chair. So the first 2 lines that you'll draw will point to the upper left-hand corner instead of the right, and then the rest of the steps are the same. You'll draw one line from the top left to the bottom right, and another line from the bottom right to the top left. Then connect the dots. After drawing the skeleton, we'll number the carbons starting from the bottom right, still going around the chair clockwise. Now the direction of bromine will remain the same, meaning it will still point downwards, but the bond type will switch from equatorial, as seen in conformation number 1, to axial in conformation number 2. And between the two conformations, number 1 is more stable than number 2 because bromine prefers to be in the equatorial position since it is large and bulky. When comparing two chair conformations, the more stable conformation with equatorial substituents will always be favored. In this example, compare the stability of the two chair conformations of 1-ethyl 3-methyl cyclohexane. Substituents that are on dashed bonds will point down in the chair. So if we draw the first chair skeleton, the downwards positions on C1 and C3 are both equatorial bond types. But if we flip the chair and draw the second conformation, the downward positions on C1 and C3 are both on axial bonds. So this means that conformation number 1 is more stable because both methyl and ethyl substituents are on equatorial bonds. Now let's look at a trisubstituted cyclohexane. Substituents on dashed bonds will always point down, and substituents on wedged bonds will point up. So let's number the cyclohexane in the original molecule first. Next, let's draw the skeleton of the first chair conformation. The chloro group is on C1 and is pointing downwards, which means it will also be on an equatorial bond. The ethyl group on C3 is pointing up, which means it'll be on an axial bond. And the methyl group on C4 is pointing down, which means it'll also be on an axial bond. Now, if we flip the chair, remember that the bond directions stay the same, but the bond types flip. So the chloro group on C1 is still pointing down, but now it's on an axial bond. The ethyl group on C3 is still pointing up, but now it's on an equatorial bond. And the methyl group is pointing down, but now on an equatorial bond. So if we compare these two chair conformations, number 2 is more stable than number 1 because substituents are on equatorial bonds.